This video will cover section 2.4, the product and quotient rule. The objectives of this video will be to review the product rule, the quotient rule, and applications in business and economics such as average cost and average revenue. Let's start by reviewing the product rule. The derivative of the first factor times the second left alone plus the first left alone times the derivative of the second. This can be extended to a product of several functions. The pattern continues. Take the derivative of each factor in turn, multiplied by all the other factors left alone, and then add them up. So because multiplication and addition are commutative, the order of these can be rearranged in that you can say f times g prime plus f prime g prime. But the goal is that you take the derivative of the first, multiply it by the second, plus the derivative of the second, times the original of the first. So this is equivalent to f times g prime plus f prime g. The quotient rule is the numerator of the result resembles the product rule, but there's a minus instead of the plus. The minus sign goes with the g prime. The denominator is simply the square of the original denominator, and there are no derivatives. So if we're looking at taking the derivative of the quotient f over g, where f and g are differentiable functions and g is not equal to 0, then we have f prime times g minus f times g prime all over g squared. It's important to note that subtraction and division are not commutative, so the order of this is important. And then another mnemonic to remember this would be low d high minus high d low all over the low squared. And there you go, where low is the denominator and high is the numerator. And when you have d, that means take the derivative. So just a little mnemonic to remember when you're taking derivatives of quotients. Let's take a look at a practice problem. In part A, we can see that we're asked to take the derivative of a quotient. I'm going to put brackets around this to note that those are all within the derivative operation. So we're looking at the factor x squared plus 1 times 7x minus 3 cubed. I'm going to go ahead and call the first factor f and the second factor g. And then I'm going to remind myself that the derivative of the product of f and g is f prime times g plus g prime times f. Again, the order of that is not as important, just as long as one derivative gets multiplied to the other non-derivative. So when we take the derivative of our function, the derivative of f using the product rule, or using the power rule, is 2x and then plus 0, and then times the original g function, plus the derivative of g will be 3 times 7x minus 3 squared, and then I'm going to put a product of 7 here. That's going to be the chain rule, which we haven't quite covered yet, but we will cover in a future section. So that would be the chain rule being applied there. Don't worry, that won't be in the homework for this section. And then we'll multiply it by the original f function, which was x squared plus 1. The rest of the work here will have to be simplification. So the final result of this problem would be 7x minus 3 quantity squared times 35x squared minus 6x plus 21. You would try to factor that trinomial if possible, but it does not factor. This would be the simplified form for part A. For part B, we're looking at a quotient. So again, I'm going to label the top function f and the bottom function g. And when I take the derivative with respect to t, that's going to be the independent variable here, of f over g, we have low d high minus high d low all over the bottom squared, and there you go. So that's going to be our goal, to take the derivative of this function, starting with g times f prime. So g is 5t plus 1, f prime is 3, minus f, which is 3t minus 2, times g prime, which is 5, and then all divided by the denominator squared, which will be 5t plus 1 squared. That's applying the quotient rule. From here, everything will be simplification of the result of that. And so the simplified form will be 13 over 5t plus 1 squared, making sure to simplify as much as possible for each derivative. Let's take a look at some business and economics applications of these ideas. The average cost for Q items is the total cost divided by Q. Remember, total cost is your fixed cost plus your total variable cost. So I'll just write that down as a reminder from the previous video. Fixed cost plus your total variable cost as a function of Q, and then we'll divide that by Q. You can also talk about the average fixed cost, which would be fixed cost over Q, or the average variable cost, which is total variable cost over Q. And you're allowed to do that because you can divide each term in the numerator by the single term that's in the denominator. This is an okay operation to take. Similarly, the average revenue for Q items is the total revenue divided by Q. We already know that we can find average rates of change by finding slopes of secant lines. Average cost, average revenue, marginal cost, and marginal revenue are all rates of change, and we can find them with slopes too. So marginal cost and marginal revenue would relate to slopes of tangent lines because those are found by derivatives. Average cost and average revenue would be similar to the slope of a secant line because it would cross through 2 points of the graph instead of just touching it like a tangent line would. Average cost is the slope of a diagonal line starting from the origin 0, 0 and going to the point Q and the total cost of Q. So here we're talking about this red line, this red dotted line. Notice that it starts at 0, 0 and it goes all the way to the end of the total cost function. Average revenue is the slope of the line that starts also at 0, 0 and then goes to Q, TR of Q, so the blue line here. So total revenue in this case is below total cost. The average total revenue is below the average total cost. Let's take a look at an example. A manufacturer has determined that an employee with D days of production experience will be able to produce approximately P of D items, where P of D is 3 plus 15 times the quantity 1 minus E to the negative 0.2 D. We want to graph P of D. From our graph, we'll approximate how many items will a beginning employee be able to produce each day? How many items will an experienced employee be able to produce each day? What is the marginal production rate of an employee with 5 days of experience? Part C will require some calculation. If we're looking at marginal production rate, we're asked to find a derivative. So whenever you see the word marginal, you want to think take derivative. Okay, let's take a look at the graph of P of D. So in Desmos, I've graphed P of D on the left-hand side. You can see my function. I'm going to go ahead and let's take a look at the graph along with the question. So approximately how many items will a beginning employee be able to produce each day? Remember that D represents an employee that has D days of production experience. So a beginning employee would have about 0 days of experience. So we're looking at about where the graph crosses the y-axis here, so the y-intercept, which would be that when they have 0 experience, they can produce about 3 items per day. So with little to no experience, an employee will be able to produce about 3 items per day. That could have been found as well using the equation by plugging in 0. How many items will an experienced employee be able to produce each day? That's going to be about where the curve levels off, because if they're experienced, they've been working for 20 or more days. If we look at 20 and then just let our point continue to go towards 25 and beyond, we're approaching what we would call a horizontal asymptote. And that horizontal asymptote occurs when y equals 18. And that comes from knowing transformations of the graph of E. So using transformations of the graph of E. So what we can see is this graph approaches and doesn't quite touch 18, but that would be the maximum number of items an experienced employee would be able to produce each day. So numerically, we could represent that by using limit notation, and that would be the limit as D approaches a large number, we could say infinity, of P of D, and then take that limit using our limit laws that we discussed earlier in this course, and it would approach 18, that horizontal asymptote. So limits are a way of checking asymptotes. For part D, we're asked to find the marginal production rate, and so we'll be looking at the derivative of the function. Okay, so marginal production rate will be the P prime of D. Let's start by distributing the 15. And then we can take the derivative from there to not get confused. What I'm looking at is the derivative of 18 is 0. and then minus 15 e to the negative 0.2d, and then times negative 0.2. That's going to be the chain rule. Again, we'll cover that in the later section. So although you can't take the derivative of this yet, there will be applications for this section where you can take the derivative in your homework. So the production rate after d days is 3 times e to the negative 0.2d, and we're asked what is the production rate of an employee that has 5 days of experience. So we'll evaluate this derivative at 5. This would be the items per day And so the way we'd interpret this is that when an employee has been working for this company for 5 days, the rate at which they can produce items is increasing 1.1 items per day per day. So it's a rate of change, or the slope of the tangent line, when they're working at exactly 5 days. In the next video, we will cover the chain rule in which we use this technique in a couple examples from this video.